A good section of track sits on clean, dry ballast, but foul the ballast with fines and water and suddenly the foundation's gone. How do you get from one to the other? The answer lies in a hidden system: drainage. When drainage stops doing its job, clean ballast turns into wet beds, standing water and geometry faults follow soon after. In this video, I'll take you through the ways drainage systems fail and, more importantly, the key design factors that keep them working. Drainage is a railway system that sits below the surface, silently fulfilling its role. It keeps the track free from one of its main threats, water. But when it fails, and the water isn't moved away, then problems for engineers escalate quickly. Water causes problems in the ballast and formation by changing how the track is supported. As water builds up, support beneath the sleepers weakens, allowing the ballast and the sleepers it supports to move under train loads. That movement pumps fine material up into the ballast, clogging the voids. As the ballast shifts and grinds against itself, it breaks down faster and creates even more fines. These fines then mix with water to form a paste-like slurry that blocks the ballast's natural drainage, trapping water in the track bed and making the problem worse. So the cycle gets worse and worse. This all leads to a loss of support for the track geometry faults, and more work for maintenance teams. The hard part is that solving the problem then becomes bigger in both scope and cost the longer it's left. Drainage can fail in a handful of common ways: collapse, blockages, weak joints, failed outfalls, and overwhelm. Let's take them one by one. Collapse. Pipes buried under the track or alongside it aren't invulnerable. Over time, they can collapse through aging, material fatigue, such as clay pipes in some older systems, or poor bedding in. Train loads also transfer through the ballast and formation onto the pipes, adding stress that can hasten failure even though the pipes aren't directly below the track. Once a section collapses, the water has nowhere to go but back into the track bed. Blockages. Even intact pipes can fail if they become blocked. The two main causes are silting and roots. Silting happens when fine material or mud builds up in catch pits or the pipes themselves until the flow of water stops. Roots are slower but just as damaging, growing into the pipe and forming root balls that trap more debris and then speed up blockages. Joints. Just as rail joints are weak points, so are pipe joints. Misaligned or damaged joints, whether between pipes or at a catch pit, disrupt water flow and create easy entry points for both silt and roots. Over time, these small weaknesses can grow into full blockages. Outfalls. A drainage system is useless if the water has nowhere to go. This could be caused by an issue at the outfall, blocked by vegetation or debris, or feeding into a downstream system that doesn't have enough capacity. When that happens, the water backs up through the pipes and stays in the track bed. Overwhelm. Finally, the drainage system can simply be overwhelmed. The pipes are sized for a certain flow rate of water, but prolonged heavy rain can exceed that capacity. When there's too much water, the system is swamped and flooding follows. Those are the ways that drainage can fail. But what actually drives those failures? It's not always one thing. It's usually a mixture of factors that make the system more vulnerable. Some of those are design choices made at installation. Others are about how the asset's maintained over time. And there are 5 that come up time and time again. There are 5 main factors in either the design or maintenance of the drainage system that can make these failures more likely. Let's start with the first: run length. A run is a length of pipe between catch pits. The longer the stretch of pipe between the catch pits, the harder it is to keep an eye on. Those catch pits are there to trap silt and debris, and it's a lot easier to clear that out in a catch pit than in a buried pipe. But if they're too far apart, you lose regular inspection points. Fines also have to travel longer distances before they're intercepted, which increases the risk of silting within the pipes and larger build-ups when material finally reaches those catch pits. Gradient. The slope of the pipe makes a massive difference. Too shallow and the water crawls along at a slow speed, letting silt settle out in the pipe and choke the system. Too steep, however, and the speed of the water gets too high. It scours the inside of the pipe, erodes joints, and can even damage the outfall where it discharges. What you're aiming for is a sweet spot engineers call a self-cleaning velocity. Fast enough to keep fines moving, not so fast it destroys the system itself. Pipe size. Bigger pipe, more water. Simple enough, but the bigger you go, the trickier it can get. Large pipes take up space, usually need to be installed deeper, and that means more cost and more chance of clashing with other buried services. Go too small though, and the first heavy rain can overwhelm the system, so again, it's a balancing act. Outfall. Outfalls are often decided early on, and that's where a lot of vulnerability gets built in. If the capacity of the receiving system isn't properly understood and up to it, if the levels don't work, or if access for inspection and maintenance of the outflow isn't designed in, the drainage system is left exposed. Everything upstream depends on that discharge point working, so any weakness there affects the whole system. Maintenance. Finally, there's maintenance. Because it's buried, drainage is easy to forget about. Catch pits slowly fill up and need clearing, but too often that only happens once a failure has already shown itself. By then, you might already have fouled ballast or a damaged formation, and then the fix is 10 times the job it could have been. The shift away from staff walking the track to train-borne inspections hasn't helped either. Fewer eyes on drainage means fewer chances to spot problems early. So those are the main factors in design and maintenance that make drainage more likely to fail. You'll notice I've mentioned fouled ballast and track geometry a few times, because drainage failures usually show up as wet beds, and those lead to geometry faults. But what do we actually mean when we talk about track geometry? If you want an easy to follow introduction to track geometry, I've put together a free email course called Horizontal Geometry Basics. It walks through the core concepts step by step, and you can sign up through the link in the description or in the top right hand corner. And it's free. Now, back to drainage. How do you design it so those failures don't happen in the first place? So we've looked at the factors that can set drainage up to fail, but what does it look like when it's done well? Let's flip it around and talk about how to design it right. Start with the outfall, because if the water can't get away, nothing else matters. The outfall needs to have the capacity to take what the system is delivering. It has to be set at the right level to allow the water to flow straight out, and it has to be something you can actually maintain. No blocked ditches or inaccessible outlets. These are guaranteed trouble. Then comes the pipe itself. Size sets the system's capacity. It has to be big enough to deal with heavy rainfall, the sort of 1 in 100 year storm that might be built into design standards, but not so big that becomes unbuildable, clashes with other assets, or costs a fortune to install. This is always a trade-off between resilience and practicality. The gradient needs just as much thought. Too shallow and you'll end up with silting up in the pipes. Too steep and the water velocity gets so high it scours the pipes, damages your newly formed joints, and batters the outfall. The aim is that sweet spot where the system is self-cleaning but not self-destructing. Catch pits are what makes the system maintainable. They need to be spaced regularly enough that silt can be intercepted and the pipework can be inspected. And they need to be sited where they won't be buried by ballast or damaged by track work. Get this wrong and the whole system becomes unmaintainable or can disappear from sight completely. And finally, you can't design maintenance out. Even the best system fails if it's not looked after. There is no such thing as maintenance free. A planned regime to inspect and clear the catch pits and the outfall is always going to cost you less and cause less disruption than waiting for failure to force you into emergency work. Regular inspections are what spot issues early, and regular cleaning is what stops issues turning into failures. When it comes to drainage, the principle is simple. If it isn't designed and maintained properly, you don't just end up fixing the drain, you end up rebuilding the ballast and formation it was meant to protect. Get it right though, and the drainage quietly does its job. By keeping water out of the ballast, it helps prevent wet beds, keeps the track geometry tight, and saves engineers a huge amount of work. Not bad for an asset that spends most of its life buried and completely out of sight.